In this video, we're going to look at molarity as a measure of concentration of a solution and a way of determining how many moles of a solute there are dissolved in a solution. We'll also see at the end of the video how we can use molarity as a conversion factor to do stoichiometry problems. First off, the symbol for molarity is a capital M or a capital M with an underline. The formula for molarity is how many moles of solute divided by the volume of the solution measured in liters that it's dissolved in. This sets up a proportionality so that we can make a solution that has any volume and change that volume, and the moles will change proportionally based on what the molarity is. A shortened version of this is molarity equals moles divided by liters. We can also use molarity as a conversion factor. Because it is a proportionality and the number of moles and the volume are going to change proportionally for a specific molarity, we can say that a 3 molar solution of silver nitrate would have 3 moles of silver nitrate in 1 liter of that solution. If we change the volume, we will change the number of moles proportionally. For example, if I had 2 liters, we would have to have 6 moles of silver nitrate, because the proportion is 3 moles of silver nitrate to 1 liter of solution. We could also go down. A 0.3 moles of silver nitrate would have a volume in a solution of 100 milliliters or 0.1 liters. Again, a 3-to-1 ratio. To see how it's used in a conversion, let's say we have 273.6 milliliters of 3 molar silver nitrate. We would have how many moles of silver nitrate? The first step is to convert our milliliters into liters. Now that we're in the unit of liters, we can use the conversion of liters and moles from our molarity to do the final step. In 1 liter of solution, we will have 3 moles of silver nitrate. So we set up the conversion so that our liters cancel out, leaving us with moles, and our answer would be 0.821 moles of silver nitrate. Now this should make sense. Our molarity is 3 moles per liter. We have less than 1 liter of solution, so we should have less than 3 moles of silver nitrate. Our proportionality allows us to make this conversion. Here's some more examples of, in the lab, different solutions that have the same molarity. So in each of these solutions, we have 1 mole of the compounds in 1 liter of solution or 1,000 milliliters of water. In each case, the number of moles of that compound in each of these bottles is the same. So I have 1 mole of iron 3 nitrate in the bottle on the left. I have 1 mole of magnesium nitrate in the middle bottle, and I have 1 mole of copper 2 nitrate in the bottle on the right. All 3 bottles are 1 liter. They all have the same volume, so we have the same number of moles in each of those solutions. Some more examples are, in this case, iron 3 nitrate. In this case, we've got a 0.2 molar solution of that. I've listed here the 3 different ways you may see it written out. 0.2 moles per liter, that would be a measure of its concentration. 0.2 moles equals 1 liter. That's how we would use its molarity as a conversion factor between moles and liters. And we could also make a conversion as 0.2 moles equals 1,000 milliliters. This makes the conversion a little simpler because most of the time we are using milliliters as our volume. If we continue down the line, we will see a similar setup. In my hydrochloric acid, it's 12 molar. That means there's 12 moles of hydrogen chloride dissolved in 1 liter of water. As conversions, we have 12 moles equals 1 liter and 12 moles equals 1,000 milliliters. Similar situation for these 2 bottles. In this case, they both have a concentration of 0.1 moles per liter. In the last bottle, we have 0.002 moles per liter of potassium thiocyanate in this bottle. Or we have 0.002 moles in 1 liter or 0.002 moles in 1,000 milliliters. Now you'll notice that the bottle on the right is much bigger than the other bottles. Yet we can still use the same concentration ratios because it is a ratio. Even though the volumes are changing, none of these bottles have 1 liter in them. The proportionality of moles to their volume is going to be the same. So if I had a larger volume of my iron 3 nitrate, which was 0.2 moles per liter, it would still be 0.2 moles per liter. I would just have more moles because I have more volume. And let's see how these can be used to solve a stoichiometry problem. If I have these two solutions, a 0.1 molar solution of sodium hydroxide and a 0.1 molar solution of calcium nitrate, if I took 75 milliliters of the sodium hydroxide and I were to mix it with the 50 milliliters of the 0.1 molar calcium nitrate, what mass of solid will form when these are mixed? The first thing we need to do is write out a chemical equation for this reaction. And we'll see that we get calcium nitrate in the aqueous form is going to react with sodium hydroxide, again in the aqueous form. They're going to form calcium hydroxide solid, and we will also get sodium nitrate as a product, but it's going to stay dissolved in the solution. The second thing we do is our stoichiometry. And as in all stoichiometry problems, we've got to convert to the unit of moles first if we're not already there. And in this case, we aren't. The only thing that we know about our two compounds is that we have the number of, or the volume, and what their molarities are. Our first step is to convert that volume into moles. And we have a conversion to go between moles and volume. In this case, I'm using that 1,000 milliliter version so I can skip a step and not have to worry about converting from milliliters to liters. In this case, 0.1 moles of sodium hydroxide in 1,000 milliliters. Our milliliters will cancel out, leaving us with moles. And that's the very first step that we have to do in every stoichiometry problem. If you don't have moles, get to them. Because now we can do our mole to mole conversion. There are 2 moles of sodium hydroxide in this reaction for every 1 mole of calcium hydroxide. And the last step, converting that moles of calcium hydroxide now into grams of calcium hydroxide. So we just look up the mass off the periodic table of calcium hydroxide, plug it in, and solve this problem. And we get 0.278 grams of calcium hydroxide. Now that's the amount of calcium hydroxide that would form from our sodium hydroxide. Let's see how much calcium hydroxide would form from our calcium nitrate. Again, we start off in a similar manner. We have to convert our volume into moles, and we use that molarity value to do that. We've got 0.1 moles, so this is 0.1 molar calcium nitrate, so we have 0.1 moles in 1,000 milliliters. Our milliliters cancel out, leaving us with moles. We can now do our mole to mole conversion, and then we can then plug in our mass and finish off the stoichiometry, and we get 0.370 grams of calcium hydroxide. Now the reason why we did both of these is because we have information about both reactants. In this case, we have the possibility of making 0.370 grams of calcium hydroxide from the 50 milliliters of calcium nitrate. We have the possibility of making 0.278 grams from the 75 milliliters of sodium hydroxide. But even though we have more sodium hydroxide, that is actually going to make less calcium hydroxide than the calcium nitrate. If you remember from first semester, this is a limiting and an excess situation. We have our sodium hydroxide being the limiting reactant because it is producing the least amount of calcium hydroxide. The calcium nitrate then would be our excess reactant because although it can produce 0.370 grams, it's not because we can only produce 0.278 grams from the sodium hydroxide. And that's it. So the stoichiometry is essentially the same as what we've been doing. The difference is how we do the conversion. And we're dealing with solutions. We have to know the molarity and the volume, and together we can use those to find moles. Once we have the number of moles, we can then use that information to find out or to do our stoichiometry.